So I have a problem here on the conservation law for a linear momentum in a control volume, and I have a steady and smooth flow of an incompressible liquid through an axisymmetric pipe. The pipe here has one inlet. This inlet is at point 1, which is shown right here, and I have one outlet, which is at point 2 here. I'm told that at point 1 the flow is given to be uniform. What do we mean by the word uniform? This means that the velocity does not change with position. On the other hand, the word steady tells me that the velocity does not change with time, or actually any other quantity. But here we're studying velocities in our equation. So we're given the values of the velocity components at the inlet. They're given as u equals u1, v is equal to 0, and w equals 0. So this is a one-dimensional velocity field. And we have a pressure of P1 that is measured at point 1. At position 2, an outlet exists. The flow is fully developed here. It's not a uniform flow then at the outlet. This is my outlet here. The flow has a parabolic shape. The pressure at point 2 is given by P2, and the x component of the velocity at P2 is given by the below expression. So this is our expression for the velocity at the outlet. This is just the x component. Now, V2 and W2 are not necessarily 0, but they're not given to us. Our question is, use the general form of the momentum conservation law for a control volume to find the total friction force exerted on the liquid by the pipe wall between positions 1 and 2. So we want to find the total friction force. I can draw it here for you. The friction will be along all of the borders of our pipe, and they will be opposing the flow. Our flow is to the right, so the friction will point to the left. Now, the general form of the momentum conservation law is given here. Remember, we found this law by studying the conservation of linear momentum and using Reynolds transport theorem to transfer from the system conservation law of linear momentum, which simply tells us that dp by dt is equal to the sum of forces. And then by Reynolds transport theorem, we obtained the conservation law for a control volume, which looked like this. This is our general form, which is an integral form. Now, of course, we can do some approximations in which we use well-defined inlets and outlets and change this integral into summations. Now, in this problem, I do have well-defined inlets and outlets, but I was specifically asked to use the general form instead of the one with summations instead of integrals. So I'm going to actually just use the integral form and try to see if I can obtain the quantity of request, which is here the friction force. Now, where can I find the friction force in this equation? It will be plugged here inside the sum of the forces acting on my control volume. Let's try to expand our equation and then simplify it. For a start, let's look at the net forces that are exerted on my control volume. Now, since I am interested in the friction force, which I can see here is essentially a horizontal force, I can directly project this equation along the x-axis. This conservation law contains vectors rather than scalars, and so in order to be able to work with this equation, I need to project along the different directions and resolve my vectors into components. So I will project along x because my friction is in the x direction. And this is the quantity I want to find. So what forces do I have in the x direction? Now, from the derivation of the momentum equation, we have discussed the forces that I usually expect to find that are acting on a control volume. And we actually resolved this sigma f into the forces that are due to first gravity, plus the pressure forces, plus the viscosity forces, plus some other forces. This is the situation where I have some external force acting on my control volume. We said we can also see external forces if we are cutting through our pipe or section that is containing our control volume. Here, I have chosen the control volume to be within my pipe, so I'm not cutting through the pipe, so I don't have any external forces due to cutting through the container, and I don't have external forces that are given to me. I'm not told that there was some pushing force exerted in this region, so I will not have any of these forces actually, and my gravity force is also not along the x direction, so I can also cancel this out because it does not have an x component, and I am essentially projecting along the x direction. This leaves me with the pressure forces and the viscosity. If I discuss the net pressure forces, I can take the difference in the pressure between the inlet and the outlet only, whereas the rest of the pressure forces will just cancel out. So for the pressure force, I can now substitute sigma f pressure by P1A1 minus P2A2. Now, let me show you how I found the signs. So any pressure force is equal to the pressure itself times the area. At the inlet, my pressure force looks like this. Whereas at the outlet, the pressure force looks like this. This is essentially because I have a control volume, and on the control volume, I will have the pressure forces always pointing into the volume itself. So P1A1 will point to the right towards the control volume and perpendicular to it essentially, whereas P2A2 will point towards the control volume again, which will be now to the left, and it's also perpendicular to the surface. And this will lead to having the following net pressure force exerted on my control volume. The pressure P1A1 from the inlet points to the right, which means it's a positive quantity in terms of the x components, whereas P2A2 is to the left, which means it will have a negative x component along the x direction. That's why I got the following term for the pressure. For the viscosity forces, I only have the friction, which is what I want to find, the total friction exerted on the liquid by the pipe wall. The friction, as you can see, opposes the fluid flow, so I have drawn it to be pointing to the left, and this basically tells me that its x component is going to be negative. So I will also have here a value minus F for my friction. Let's write down how my equation now looks like. I got P1A1 minus P2A2 on the left side minus the friction force. On the right side, I have a steady flow, so I can directly cancel this term, and I'm left with the integral over the control surface. Now, this integral over the control surface basically tells me about the net flow rate out of my control volume. So I can basically keep it in an integral form, but split it over the inlet and the outlet. So I'm going to split this integral into two integrals, one over the inlet and one over the outlet. The one over the inlet will have a minus sign because this integral is the net flow rate that is out of my control volume. So anything that is coming in will have a negative flow rate. And I will leave things in terms of the integral and the vectors. Now I am projecting along x, so this vector here will resolve into u. Whereas here I will still have the dot product because this is not really going to be a vector anymore. And over the outlet I have the same thing. Now my inlet and outlet are defined as points 1 and 2 in this problem. You can see that in our figure. This is my inlet, it's at point 1, and my outlet is at point 2. Now I can actually define these as U1 v1.n dA1 u2 v2.n dA2. Okay, v1.n will basically be the dot product between the normal to the surface and v1. I can see that v1 is already obviously perpendicular to the area of the cross-sectional area of my pipe, so v1.n will just give me u1, which is the x component of my velocity. And v2.n, this is also the x component of v2, which is basically u2, which is given here, by the way, and it's not really uniform, but I can just substitute v2.n now by u2. Now we can see that the areas A2 and A1 are the same across my pipe. My pipe does not narrow, does not converge or diverge, so the areas are the same. I can just leave this as dA. I also know that U1 is actually uniform. You can get back to the figure and see how U1 does not depend on position. So actually I can just take this outside my integral. And this will end up with just an integral over dA, which is basically just the cross-sectional area of my pipe itself. Over my outlet, however, I can only take rho to the outside, but U2 itself, it varies with position, so I cannot really take it outside my integral, and I will have to write dA in terms of some infinitesimal area. Now, my pipe cross-section looks like this, so an infinitesimal area over which I can integrate can actually be this string of thickness dr and radius r. So dA can actually be written as 2 pi r dr, which is the circumference of the ring times its own thickness. And now my equation will look like minus rho u1 squared a plus rho integral. What is u2? I have the expression of u2 over here. It is u maximum into 1 minus small r squared over capital R squared. And I will substitute dA, which is 2 pi r dr. I will obtain minus rho u1 squared a plus rho u max. I have a square here, sorry about that. I'll take 2 pi to the outside as well, and now I have 1 minus r squared over capital R squared squared times r dr. I got minus rho u1 squared a plus rho u max squared times 2 pi integral of, now I will expand this identity and I will multiply by r once I finish expanding this expression. So basically you should get r minus 2 r cubed over r squared plus r power 5 over r power 4 dr. And this integral should go from 0 to capital R. So from here it's quite straightforward for us to solve the integral and then be able to rearrange our equation to obtain the friction force. I have here our form of the equation that we have reached so far for the conservation of linear momentum, and to solve the integral this is very straightforward. I'll get r squared over 2 minus 2 r power 4 over 4r squared plus r power 6 over 6 r power 4, and all of these are between 0 and capital R. This will basically give me, so this is, we're just solving the integral here. This is going to give me capital R squared over 2 minus 2 r power 4 over 2r squared plus r power 6 over 6 r power 4. This is after I substituted capital R and 0 as my boundaries for the integration. You can see how this will give me r squared over 2 minus r squared over 2 again plus r squared over 6. So our answer is actually r squared over 6. This is the answer of our integral. And then I can write my new equation. I have P1 minus P2A minus the friction force, which is what I want, equals minus rho U1 squared A plus rho U max squared times 2 pi R squared over 6. Now, you can see how I have things in terms of U1 and U max. I can actually stop here and leave them, take some commons. Pi R squared that I have here is the area. So I can take rho and A as common, and I'll have in here minus U1 squared plus U max squared over 3. You will see that in the next video, in which I try to solve things in terms of the equation that has well-defined inlets and outlets, that U maximum is actually equal to twice U2 average. Here, of course, we're talking about U2 max. And you will see that in this problem in particular, U2 average is equal to U1 itself, because I have well-defined inlets and outlets, and U1 here is uniform, whereas U2 has this profile, but the average of this profile must essentially be equal to the average of the inlet, which is U1 itself. So U2 average is equal to U1, and U2 average is also equal to U2 maximum over 2, as I have just written here. So this will further reduce my equation. So I'll substitute U maximum by 2U1. So I'll have 4U1 squared over 3. And this gives me rho A U1 squared over 3. And I can rearrange for the friction, which is what we want in this problem. I'll have P1 minus P2 minus rho U1 squared over 3 times the area. I'm given the area in terms of the radius, so it's better that I substitute things in terms of the radius as well. And this is basically my expression of the friction force that is exerted by the pipe on the flowing fluid inside of it.